Welcome to the course of analysis of several variable, and we continue with the chapter 4 partial derivative and directional derivative. So this is the fourth part, and in this lecture we are going to discuss about the directional derivative. We start with the definition of the directional derivative. So for that we need an open set omega on Rn and a point A in the omega, and f is a function from omega to Rm, and v belongs to Rn is a vector in which directions we are going to define the directional derivative. So we say that f has a directional derivative at A with respect to the vector v if the limit t tends to 0, f a plus tv minus fa over t exists. So if this limit exists, then we have a directional derivative of the function f along at the point a along the vector v, and the value of this limit is the value of the directional derivative. Now the notation for this generally use dvfa. So that is direction derivative of f at the point A along the direction of v, and this is equal the limit if the limit exists. Now in particular, if we take v is equal ek, so v is equal ek, while ek means 0, 0, 1, 0, 0. So kth vector is kth component is 1. Then this directional derivative is same as the partial derivative of f with respect to the variable xk. So if you take e1, that means 1, 0, 0, then de1 fa is equal del f del x1 a, where f is a function, means whenever you have the f is a function x1, x2, xn, and then we will have here the component we can say. So this is, we say x. We take this is x, so it will have fx, f2 x, and then fmx. So we are taking the partial derivative of f with respect to the variable x1. Okay, so if it is e1, so same way e2 will be the partial derivative with respect to x2, and so on. So this gives us a relation between the partial derivative and the directional derivative. Now we have a theorem with associate with the directional derivative. So this theorem says that let omega be open on Rn. A is a point in the omega and f from omega to Rn. Now if f is differentiable, so this is the condition that if f is differentiable at A, then for any v belongs to Rn, directional derivative exists, and the directional derivative at A is associated with the derivative of f with this relation. Okay, so therefore differentiability implies the directional derivatives, but the opposite is not true. Hence, a particular direction's derivative does not guarantee that function is differentiable in the whole all directions and is differentiable at the point A. So the opposition is not true. So differentiability guaranteed that there will be a directional derivative at that point in any direction of the vector v, but the opposition is not true. Okay, so we'll do the numerical problem to calculate the directional derivative and all those related use of the theorems and definitions in the end of this chapter, means in the next lecture. Okay, now we move to the next topic, section 4.4, which is mixed partial derivative. So we have the partial derivative till now is del f, del x, del f, del y if two variable functions and so on, or if you have del 2f, del x2, del 2f, del y2, second order partial derivative. Now the question is, we will have the mixed partial derivative del f, del x, del x, del y, means one time with respect to y, another time with respect to x. Or we will also discuss if it is opposite, then how they are connected. So this is called the mixed partial derivative. So let's start with the definition. So it is the same way that omega is open on Rn, A is a point in the omega, and f is a function, and then we say that del 2f del xk del xi. So this is a mixed derivative with respect to the variable xk and with respect to the variable xi. Exist if del f del I exists for all xi, and del f del xi is partially differentiable with respect to xk at a. So first we'll calculate del f del xi. So it must exist. Okay, and then whatever the new functions will come with respect to all the variables from x1 to xn, then the new function is also be differentiable with respect to the partially differentiable with respect to xk at a, then the mixed partial derivative will exist. Okay, so we can say that this can be written as like this: del 2f del xk del xi operating on a is equal, first we'll calculate the partial derivative of f with respect to xi, then we'll take the partial, we'll get the new function, and then we'll take the partial derivative of the new functions with respect to the variable xk, and then put the value of the point a and calculate the value of the function derivative. Okay, so if it is opposite xi xk, then you have to take the first with respect to xk and then with respect to xi. Now the natural question is this: are they always equal? The answer is no. They may not be always equal. Okay, now we have a function here. Then it says that the function is from R3 to R, defined as ln 1 plus x square z square plus y square, and we have to find del 2f del z del x at the point 1, 0, 2. So first we ignore the point and we calculate it the derivative, and we'll see that how it will come. You cannot use that earlier definitions that we will take the all the point. For example, we are taking first partial derivative with respect to x, so we just substitute the other variables value and only keep x, then you will get the derivative. So that will be not possible here, because we have to do first all the derivative and then we have to apply the point here. So we'll calculate it in this way. Solution. So first we need to calculate del f del x. This is equal. So derivative of ln 1 plus x square z square plus y square. So we know that we'll use the chain rule. Derivative of the ln will be 1 over 1 plus x square z square plus y square, and then partial derivative of the inside variable. Now when we do the partial derivative with respect to x, other will be constant. So therefore we will have this is 0. This is only you have 2x z square and this is 0. So we will get it here 2x z square over 1 plus x square z square plus y square. Now we will take the partial derivative of these functions with respect to z. So next is del z del f del x. So this is equal del z, and we have here 2x z square plus 1 plus x square z square plus y square. So this is del f del z. Now since this is the last step, so we can use this point. So you have to do it at 102. So this can be done as, so we can put the value of x and y and keep z as it is. So therefore we'll get it here. X is 1. So this will be 2 z square over 1. X square is 1. So it is z square. Y is 0. So this is like this at the point now z is equal to. So therefore we get the derivative. What will be the derivative here? 1 plus z square whole square. To add is like this. So this is 2z and then 1 plus z square minus, then we'll have here 2 z to the power 3 at z is equal to. So we substitute the value 2, and this will be 2 multiplied 2, 1 plus 2 square minus 2, 2 to the power 3, 1 plus 2 square whole square. So this is equal to, and then it is 4 and this is 5, 20 minus this is 2 and 8, 16, and denominator is 4 plus 1, 5, 25. So this is equal 20 minus 16, 4, 8, 8 over 25. So here you can, in this part, without substituting these points, you can calculate all the partial derivative, and then also you can substitute it in the end, and you will get the same answer. So the answer is 8 over 15. Okay, now we have here one definition is about the function is type Cn. Okay, and on omega or f belongs to Cn omega, where n is the natural number including infinity. We can say extended set of natural number, and this is the f type of Cn. We already defined C1. C1 means all the first order partial derivatives should be continuous. Now naturally the Cn will be all the nth partial derivatives should be continuous. Now when we talk about the nth partial derivative, then it will come to the mixed derivative also. So this definition is that if all the partial derivative of f of order less or equal to n are continuous. So when we say that C2, okay, and let's say, So f belongs to C2. This means all the partial derivative of f of order 2 or less are continuous. Means first order and second order partial derivative should be continuous. Now if f is a two variable function, so we will have del f, del x, del f, del y, del 2f, del x2, second order partial derivative, del 2f, del y2, and del 2f, del x, del y, del 2f, del y, del x. All these should be continuous. Then we can say f is belongs to C2. Okay, so therefore, with this continuations means C0 means function should be continuous. C1, the first order partial derivative continuous. C2, all the second order partial derivative continuous, and so on. So C infinity will be all kind of the partial derivative should be continuous. So therefore, this is the smallest set. Okay, how much conditions will increase? That will be the smallest set. So C naught is function is continuous only. C infinity is all kind of the partial derivative of any order should be continuous. So this is the smallest set. Okay, now if we have a f belongs to C to infinity, means if the function is C to infinity, then the partial derivative, second order partial derivative with respect to two variables are equal. So therefore, if f belongs to C2 and f is a function of two variable xy, then del 2f, then del 2f, del x, del y will be del 2f, del y, del x. Means for that function should be belongs to C to infinity. So if belongs to C to infinity, then they are equal. And this theorem is known as the source theorem. Okay, so now we'll come to the next topic. Is theoretically this is the last topic, 4.5, which is the gradient of a function. So we'll again start with the definition. So gradient of a real function, sigma be open on Rn, f is from sigma to R, a differentiable function. So we are starting with the condition that function is differentiable at A. And f dash A is linear from Rn to R. So here the function is from omega to R, not Rn to Rm. It is Rn to R. So therefore, the derivative is belongs to in the set of linear Rn to R. Then from this theorem, we did it in chapter 1, there exists a unit vector. There exists a unit vector gradient. This is notation is gradient of fa belongs to Rn, such that for all h belongs to Rn, FAH is equal gradient of FAH. The gradient of FA is the notation. This gradient of F is the gradient of F at A. Now we have a theorem here that omega be open on Rn. F is a differentiable function at A belongs to. Then gradient of Fa is calculated by like this. I think there is a this is f dash ah is equal gradient of f a h. Okay. this theorem we are not going to prove it. So the gradient of fa is the partial derivative of f with respect to the each variable is known as the gradient of fa. Okay, now we have an example here. Let f is from Rn to R, defined as fx is equal absolute value of x whole square. Then the question is find gradient of fx for all x belongs to Rn. There are two methods to solve it with respect to the previous theorem. We can connect it with the gradient of means fa or fx with the derivative, or we can calculate directly using the partial derivative of f with respect to each variable. Solution here, so for all x belongs to Rn, because the function is defined on the Rn, we have fx is equal absolute value of x. So what is x? X is x1, x2, xn. The absolute value of x whole square, this will be x1 square plus x2 square plus xn square. Now if we take the partial derivative of f with respect to all variable, then it will be we can get the gradient. So here is f is kind of polynomial, so it is differentiable. And then from the previous theorem, gradient of fx is equal del fx del x1 and this fxn. So each cases, if you take the partial derivative with respect to x here, with respect to each variable, so you will get it 2x1, 2x2, 2xn. So if you take out 2, so it will be this is equal to x. So gradient of f is equal to. You can solve this one by using a chapter 3 where we will get the derivative. So if you solve it like this, so it will be f dash x h is equal to x dot h. So from the definitions we will have that this is equal gradient of fx dot h is equal to x dot h. So comparing this, we'll get it gradient of fx is equal to x. So this way also you can show it, but for that you have to show that calculate the derivative using the definition of the derivative. Then you can apply this theorem. So this is, we can say, method 2, but this is the method 1, which is the easy method. Okay, so this finished the theoretical part of this module, chapter 4, and next lecture we will have the examples related to the chapter. So all kind of the examples, 4-5 examples involving the mixed derivative, partial derivative, directional derivative, gradient, and their connections. We'll solve numerical problems together in the next lecture.